Imagine standing at the edge of time itself, gazing back into the universe's very first light, a faint, ancient glow that has traveled across billions of years to reach us. This is the cosmic microwave background, or CMB, the oldest light in existence, and it holds secrets about the birth of everything we know. Picture this: the entire sky is filled with a whisper of radiation, a cosmic fingerprint left over from the Big Bang. It's not just light, it's a time machine, a window into the universe's fiery infancy. And today, we're diving deep into 25 astonishing facts about this celestial relic, facts that will reshape how you see the cosmos. Why does this matter? Because the CMB isn't just some distant curiosity. It's the foundation of modern cosmology. Without it, we'd have no way to test our theories about the Big Bang or understand how the universe evolved from a searing hot soup of particles into the vast, structured cosmos we see today. Every tiny fluctuation in this ancient light tells a story of gravity's first tug, of the seeds of galaxies, even of the mysterious dark energy pulling the universe apart. It's like reading the universe's diary written in the language of microwaves. But here's what's truly mind-blowing: this light is everywhere. Right now, as you watch this, remnants of the Big Bang are passing through you, invisible but undeniable. It's a humbling thought, isn't it? We're all bathed in the afterglow of creation, and over the next few minutes we'll unravel its mysteries together. From how it was accidentally discovered by two radio astronomers to why its temperature isn't perfectly uniform, and what that means for the fate of the cosmos. So buckle up, this isn't just a journey through space, it's a voyage back to the very beginning of time. The cosmic microwave background isn't just old, it's the universe's baby picture, captured when everything was a mere 380,000 years old. To put that in perspective, if the cosmos were an 80-year-old person, this light comes from its first 3 days of life. Before this moment, the universe was too hot and dense for light to travel freely. Atoms hadn't even formed yet. It was just a swirling plasma of protons and electrons trapping photons in a cosmic fog. Then, as things cooled, the first atoms emerged and light finally broke free. That flash, stretched by 13.8 billion years of expansion, is what we detect today as the CMB. The story of its discovery reads like a scientific fairy tale. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent hiss in their antenna at Bell Labs. They scrubbed off pigeon droppings, recalibrated equipment, but the noise wouldn't vanish. What they'd stumbled upon wasn't interference, it was the echo of creation itself. Their accidental detection settled one of astronomy's fiercest debates. The universe had a fiery beginning. The steady-state theory, which claimed the cosmos had no start, crumbled overnight. Suddenly, we had proof that everything began with a bang. Here's what makes this glow so extraordinary. It's not just ancient, it's everywhere. No matter where you point a telescope, you'll find this microwave whisper bathing the universe in near-perfect uniformity. But hidden within that smoothness are tiny fluctuations, warmer and cooler spots no bigger than 1 part in 100,000. These minuscule variations are cosmic gold. They're the imprint of density differences in the early universe, the gravitational seeds that would one day grow into galaxies and clusters. Without them, the cosmos would have stayed featureless forever. Think of the CMB as the ultimate time capsule. It's not merely light, it's a snapshot of the universe's structure at a specific moment, frozen in microwaves. The patterns we see today, those faint temperature differences, are the blueprints for everything that followed. They reveal how matter clumped together, how space itself stretched, even how fast the universe expanded. And here's the kicker, we're still decoding its secrets. Modern telescopes like Planck and WMAP have mapped it with such precision that we can now measure the universe's age, composition, and fate from this primordial afterglow. What's truly humbling is realizing we're made of the same stuff as this ancient light. The atoms in your hands, your screen, even your eyes, they were forged in that same primordial furnace. When you look at the CMB, you're not just observing history, you're seeing your own origin story written across the sky. One of the most baffling things about the cosmic microwave background isn't just its age, it's how eerily uniform it is. Imagine baking a cake so perfectly even that every slice, no matter where you cut, has almost identical texture and temperature, now scaled that up to cosmic proportions. The CMB's temperature hovers at 2.725 Kelvin everywhere we look, with deviations so slight they're like comparing a single grain of sand to an entire beach. Those tiny fluctuations, just 1 part in 100,000, are the only breaks in this cosmic symmetry. This near-perfect uniformity tells us something extraordinary about the early universe. In its infancy, matter and energy were distributed with almost unimaginable smoothness. But here's the puzzle. Regions of space now billions of light-years apart share the same temperature, even though there hasn't been enough time since the Big Bang for heat or light to travel between them. How could they synchronize so perfectly? Enter cosmic inflation, the theory that the universe underwent an exponential growth spurt in its first fraction of a second. Inflation stretched space itself faster than light could cross it, smoothing out irregularities like a cosmic iron, leaving behind the near-uniform canvas we observe today. Think of it like blowing up a balloon with tiny dots. Before inflation, those dots might have been clustered unevenly, but as the balloon expands, the dots spread out, appearing more evenly spaced from any vantage point. That's inflation's magic. It took potential chaos and stretched it into order. Yet those minuscule temperature variations we see, they're the price of creativity. Quantum fluctuations during inflation were amplified into the slight density differences that later seeded galaxies. Without them, gravity would have had nothing to work with, and the universe would have remained a featureless void. The precision of these measurements is staggering. Satellites like Planck have mapped the CMB's temperature to within a millionth of a degree. That level of detail lets us peer back not just to the universe's childhood, but to its first trembling moments. Inflation isn't just a neat idea. It's a framework that explains why the cosmos looks the way it does. And those faint fingerprints in the CMB, they're our best evidence that the universe didn't just expand, it exploded into being with a uniformity so perfect it had to be stretched into existence. Those tiny fluctuations in the cosmic microwave background, those faint temperature differences of just 1 part in 100,000 aren't random noise. They're the universe's architectural blueprints, the hidden code that determined where galaxies would rise and voids would stretch. Think of them as cosmic breadcrumbs, leading us back to the moment gravity first began sculpting the cosmos. Each slightly warmer patch marks where matter was denser in the early universe, each cooler spot a region where it was sparser. Over billions of years, gravity amplified these differences, pulling more material toward the dense areas until they collapsed into galaxies, while the emptier regions became the vast cosmic voids we see today. But here's the twist: ordinary matter, the atoms making up stars, planets, and us, wasn't the primary force behind this gravitational tug of war. Dark matter, that invisible mystery making up 85% of the universe's mass, did the heavy lifting. Its gravity dominated the early universe, creating wells where normal matter could later pool. The CMB's fluctuations reveal this interplay in stunning detail. The patterns align precisely with the distribution of galaxies we observe today, as if we're watching a time lapse of the universe's growth from infancy to adulthood. Without dark matter's unseen scaffolding, those slight density variations in the CMB wouldn't have had enough gravitational pull to spark the formation of everything we see. The scale of this structure is breathtaking. Those tiny temperature variations correspond to regions spanning hundreds of millions of light years. a cosmic web of filaments and clusters where galaxies gather like jewels on invisible strings. Satellites like Planck have mapped this web with such precision that we can trace its evolution from the CMB's faint wrinkles to the splendor of the modern universe. It's as if we've found the universe's recipe written in microwaves, and the secret ingredient, dark matter's silent, relentless pull, turning quantum whispers into galactic symphonies. What's even more astonishing is how these fluctuations act as a universal measuring tape. The apparent size of the warmer and cooler spots in the CMB depends on the geometry of the cosmos, whether space is flat, curved, or closed. The fact that the spots match predictions for a flat universe with extraordinary accuracy is one of cosmology's greatest triumphs. It tells us the universe's total mass and energy balance perfectly, a delicate equilibrium that allowed structures to form without collapsing or tearing apart. So when you look at a map of the CMB, you're not just seeing static from the dawn of time. You're staring at the gravitational fingerprint of dark matter, the birth certificates of galaxies, and the framework of reality itself. Those subtle variations are the universe's way of whispering its deepest secrets, if only we know how to listen. The cosmic microwave background wasn't always the faint microwave whisper we detect today. It began as a blazing flash of visible light, so intense it would have blinded anyone who saw it. Over the past 13.8 billion years, the universe has stretched this primordial glow into the cooler, fainter signal we now observe. This cooling isn't just a side effect of time, it's a direct consequence of space itself expanding. Imagine the light as waves painted on a rubber band. As you stretch the band, the waves grow longer, shifting from vibrant blues and whites to deeper reds and finally into the microwave range. That's cosmic redshift in action, the universe's way of diluting its own energy as it grows. When the CMB first broke free, its temperature was around 3,000 Kelvin hotter than the surface of most stars. Emitting a brilliant orange-white light, it filled the entire cosmos with a searing radiance. But as space expanded, the light's waves were stretched, lowering its energy and shifting its color down the spectrum. By the time it reaches us, that once scorching glow has chilled to just 2.725 Kelvin, a whisper above absolute zero. This cooling isn't just a curiosity, it's a thermometer for the universe. The precise temperature of the CMB today confirms the rate of cosmic expansion, acting like a cosmic speedometer telling us how fast space has stretched over time. To grasp how profound this cooling is, picture a cup of coffee left on a table. Over hours, it loses heat to its surroundings, eventually matching room temperature. But the CMB's cooling is different. There's no outside environment for it to lose energy to the universe is all there is. Instead, the light's energy drops because space itself is diluting it, like ink spreading in an ever-growing pool of water. Every photon of CMB light has been traveling for billions of years, and during that journey, the expansion of space has sapped its energy, transforming it from visible light into microwaves. This redshift isn't unique to the CMB. It happens to all light traveling through the expanding cosmos. Galaxies racing away from us appear redder because their light is stretched just like the CMB's. But the background radiation is special because it's the most extreme case of redshift we can observe. While galaxies might shift from blue to red, the CMB has shifted entirely out of the visible spectrum, a testament to how much the universe has changed since its infancy. The implications are staggering. That cooling glow is a direct measurement of the universe's expansion history. By studying how much the CMB has redshifted, cosmologists can trace the exact rate at which space has grown, revealing not just the past but the future of the cosmos. If the cooling had followed a different pattern, it would mean space expanded faster or slower, altering the fate of everything within it. The CMB's temperature is a silent witness to the universe's relentless growth, a growth that's written in the fading energy of the first light. Among all the revelations hidden in the cosmic microwave background, one of the most profound is its silent testimony about the shape of the universe itself. Those faint temperature fluctuations we've been exploring, their size holds the key. When scientists meticulously measured the angular scale of these variations, how large they appear across the sky, they discovered something astonishing. The universe is flat. Not flat like a sheet of paper, but flat in the cosmic sense, where parallel lines stay parallel forever, and the rules of geometry we learned in school hold true on the grandest scales imaginable. This flatness isn't just a quirky detail, it's a cornerstone of modern cosmology. Imagine space as a giant, stretching fabric. In a closed universe, this fabric would curve inward like a sphere, causing parallel beams of light to eventually converge. In an open universe, it would curve outward like a saddle, making those beams diverge. But in a flat universe, the fabric remains taut and uncurved, with light traveling in straight, unwavering lines. The CMB's fluctuations act like a cosmic ruler, measuring this curvature. The most common patches of slightly warmer or cooler light appear about 1 degree across the sky, exactly the size predicted for a universe with no overall curvature. Here's why this matters. A flat universe is a direct prediction of cosmic inflation, that explosive expansion in the first fraction of a second after the Big Bang. Inflation stretched space so dramatically that it smoothed out any curvature, much like blowing up a balloon to cosmic proportions, makes its surface appear flat to an ant standing on it. The CMB's flatness is like finding a fossil of that primordial growth spurt, a relic of inflation's relentless pull. If the universe weren't flat, those temperature variations would appear larger or smaller, betraying a hidden curvature. But the measurements leave no room for doubt. Space, on the largest scales, plays by Euclid's rules. But wait, how can the universe be flat and still contain so much matter and energy? Shouldn't all that mass warp space-time? This is where things get even more intriguing. A flat universe implies a precise balance between matter, energy, and the expansion rate. There's just enough stuff to keep space from curving, but not so much that it collapses in on itself. That balance hinges on a cosmic accounting trick. The combined density of ordinary matter, and dark energy adds up to the critical value needed for flatness. It's as if the universe did the math perfectly, ensuring its geometry stayed flawless across billions of years. The implications ripple outward. A flat universe suggests it's infinite, no edges, no center, just an endless expanse of space and galaxies. It also reshapes our understanding of the cosmos's fate. In a flat universe dominated by dark energy, expansion will continue indefinitely, growing colder and emptier with time. Those faint microwaves we detect today, they'll redshift further, fading into oblivion as the universe stretches toward an unimaginable future. Yet right now, they're here, whispering the truth about the shape of reality, a truth written in the angular language of ancient light. Among the near-perfect uniformity of the cosmic microwave background lies an anomaly so striking it's been called the universe's most mysterious cold spot. Spanning a staggering 1 billion light-years, this region is noticeably cooler than its surroundings, a cosmic bruise that shouldn't exist according to standard cosmology. Imagine scanning a vast desert where every grain of sand is nearly identical in temperature, only to stumble upon a single, inexplicably frosty dune stretching farther than the eye can see. That's the scale of this enigma. The cold spot's existence throws a wrench into our understanding of cosmic evolution. Initially, scientists theorized it might be a supervoid, an enormous, mostly empty region of space where the lack of matter could subtly redshift light passing through it, creating a cooler appearance. But detailed surveys found no void large enough to explain the temperature drop. The numbers just don't add up. Even the emptiest known regions of the universe couldn't account for such a dramatic effect without rewriting physics. This inconsistency has sparked wilder possibilities. Some researchers suggest the cold spot could be evidence of a collision with another universe, a gravitational tug from a parallel cosmos imprinting itself on ours during inflation. It's a radical idea, but inflation theory does allow for the existence of a multiverse where bubble universes form endlessly. If one of those bubbles grazed ours, the energy drain might have left behind this cosmic scar. Of course, proving such a theory is nearly impossible with current technology, but the very fact it's being seriously considered shows how deeply this anomaly challenges our models. Others propose the cold spot might be a rare statistical fluke, a cosmic roll of the dice where random quantum fluctuations during inflation created an unusually large underdense region. While the odds are slim, in a universe as vast as ours, even the unlikeliest events can occur. But when simulations of the CMB's formation consistently fail to produce anything as extreme as this cold spot, the fluke explanation starts feeling like wishful thinking. What makes this mystery so compelling is its defiance. The CMB is our most precise window into the early universe, a dataset so clean it's often called cosmology's gold standard. Yet here, in its pristine map, lies a blemish that refuses to fit the mold. Whether it's a sign of exotic physics, a glimpse beyond our universe, or something entirely unforeseen, the cold spot remains a tantalizing reminder that even our best cosmic blueprints might still be missing a few pages. The cosmic microwave background doesn't just map the universe's structure, it's a cosmic ledger meticulously recording the precise recipe of everything that exists. Those subtle temperature variations we've been exploring, they're not random. They're the echoes of a universe built on a startling imbalance. Just 5% ordinary matter, the atoms that make up stars, planets, and us 27% dark matter, the invisible scaffolding holding galaxies together, and a staggering 68% dark energy, the mysterious force accelerating the universe's expansion. This breakdown isn't guesswork, it's etched into the CMB's fluctuations with mathematical precision, decoded by satellites like WMAP and Planck. Here's how it works. The CMB's temperature patterns act like a cosmic scale, weighing the universe's ingredients. Ordinary matter interacts with light, leaving distinct imprints in the microwave background's peaks and valleys. Dark matter, while invisible, exerts gravitational pull, warping the light's path in ways that reveal its presence. And dark energy, it shapes the overall smoothness of the fluctuations, stretching space itself to dilute the CMB's signal over time. When scientists analyzed these fingerprints, they found ordinary matter. The stuff we've studied for centuries is a mere sprinkle in the cosmic mix. Dark matter outweighs it 5-1, while dark energy dominates everything else. The satellites that unlocked this breakdown are feats of engineering. WMAP, launched in 2001, mapped the CMB's temperature variations with unprecedented detail, while Planck, reaching even colder orbits a decade later, sharpened the image to near perfection. Their data revealed an astonishing truth. Without dark matter's gravitational grip, the universe's matter would have been too thinly spread to form galaxies, and without dark energy's push, the cosmos wouldn't be accelerating apart. The CMB's fluctuations are the receipts for this cosmic transaction, showing how each component shaped the universe's fate. Think of it like baking a cake where the flour, ordinary matter, is barely noticeable next to the unseen leavening agents. Dark matter is the baking powder making the cake rise, while dark energy is the heat, ensuring it expands without collapsing. Remove any ingredient and the universe as we know it crumbles. The CMB's brilliance lies in its ability to measure this recipe billions of years after the fact, like deducing a chef's secrets from a single bite. What's humbling is realizing how little of the cosmos we actually see. Every telescope, every probe, every human eye has only ever observed that 5%. The rest, the dark majority, reveals itself only through gravity's subtle tugs and the CMB's whispered secrets. It's a reminder that the universe, for all its splendor, is still largely a mystery, its composition written in light we've only just learned to read. Hidden within the cosmic microwave background's faint glow is another layer of intrigue: light that doesn't just ripple in temperature but dances with polarization. Like sunlight reflecting off a lake, the CMB's photons carry a subtle directional preference, a fingerprint of the universe's earliest tremors. This polarization splits into two distinct patterns: E modes, which curl like the petals of a flower, and the far more elusive B modes, twisting like whirlpools. While E modes arise from ordinary density fluctuations, B modes could be the smoking gun for inflation's gravitational waves, ripples in space-time itself from the universe's violent birth. To grasp why this matters, picture the infant universe as a stormy sea. Inflation, that unimaginably rapid expansion in the first trillionth of a second, didn't just stretch space, it sent shockwaves through the fabric of reality. These gravitational waves would have jostled the primordial plasma, imprinting a telltale twist on the CMB's polarization. Detecting B modes would be like finding the fossilized ripples of that storm, direct evidence of inflation's ferocity. It's the difference between inferring a hurricane from debris and hearing its roar in a recording. The hunt for these cosmic whirlpools has pushed technology to its limits. Projects like BICEP and the South Pole Telescope scan the sky from Earth's most inhospitable deserts, where thin, dry air offers the clearest view of microwaves. In 2014, BICEP-2 initially claimed a detection of primordial B modes, a discovery that would have been Nobel-worthy, until interstellar dust muddied the signal. This setback underscores the challenge, distinguishing inflation's whisper from the cosmic static of dust and galactic magnetism. Yet the pursuit continues because the payoff would rewrite physics. What makes B modes so revolutionary isn't just proving inflation happened, it's revealing how it happened. Different inflation theories predict different strengths of gravitational waves. A detection would tell us whether inflation was a gentle swell or a cataclysmic surge, whether it lasted a fraction of a second or lingered longer. It's like uncovering the handwriting of the universe's first law, scribbled in spacetime's vibrations. Even without definitive B modes, the CMB's polarization has already reshaped cosmology. E modes confirmed the universe's plasma sloshed like water in a bowl before atoms formed, while the absence of certain B modes ruled out whole classes of inflationary models. Each measurement narrows the possibilities, inching us closer to answering the ultimate question: what sparked existence itself? The CMB's polarized light isn't just a relic, it's a cipher, waiting for the right key to unlock the universe's first secret. The cosmic microwave background isn't just a relic, it's the universe's first portrait, a baby picture taken moments after its birth. Imagine holding a photograph of yourself as a newborn, but instead of a crib, the backdrop is a seething ocean of plasma, hotter than the surface of the sun. That's the CMB, a snapshot of the cosmos at just 380,000 years old, capturing the exact instant it transformed from an opaque fireball into a place where light could finally escape. This pivotal moment, called recombination, marks the universe's first breath of clarity, the point where it cooled enough for protons and electrons to combine into neutral hydrogen atoms, ending their chaotic dance and letting photons stream freely for the first time. Before recombination, the universe was a roiling fog. Light couldn't travel more than a tiny fraction of an inch before being absorbed and re-emitted by the dense plasma, like a flashlight beam trapped in thick smoke. But as temperatures dropped below 3000 Kelvin, something extraordinary happened. Electrons, which had been ricocheting like pinballs, finally slowed enough to be captured by atomic nuclei. With no free electrons left to scatter them, photons burst free in a sudden flash, racing outward in all directions. That flash, stretched and cooled by billions of years of cosmic expansion, is what we now detect as the CMB. It's not just light, it's the moment the universe became transparent, a cosmic curtain rising on the stage of existence. What makes this baby picture so revealing is its simplicity. Unlike later epochs cluttered with galaxies and quasars, the recombination era was a blank canvas. The universe hadn't yet developed complex structures. It was a nearly smooth soup of matter and energy, its tiny density fluctuations, those seeds of future galaxies, still too faint to disrupt the overall uniformity. This purity lets us study fundamental physics in its cleanest form, as if we've been handed an unblemished fossil from the dawn of time. The CMB's near-perfect blackbody spectrum, its subtle temperature variations, they're the fingerprints of a universe still in its infancy, before gravity had time to sculpt it into the cosmic web we know today. Yet even in this simplicity, there's breathtaking detail. The precise wavelengths of the CMB's photons encode the exact temperature of the universe at recombination, down to a fraction of a degree. The patterns in its fluctuations reveal the speed of sound in that primordial plasma, a relic of how pressure waves propagated through the early cosmos. It's like analyzing the brushstrokes on a masterpiece to deduce the artist's tools and techniques. Only here, the artist is nature itself and the canvas is space-time. To hold this baby picture is to witness the universe's most formative moment. Every star, every planet, every life form owes its existence to that pivotal transition when light broke free and the cosmos took its first clear look at itself. And now, 13.8 billion years later, we're here to decode its secrets one microwave whisper at a time. The cosmic microwave background isn't just a fossil, it's a cosmic speedometer, helping us measure how fast the universe has been expanding since the beginning of time. By analyzing the precise patterns in the CMB's temperature fluctuations, scientists can calculate the Hubble constant, the rate at which space itself is stretching. Think of it like measuring the stretch marks on a balloon to determine how quickly it's being inflated. The CMB gives us a snapshot of the universe's expansion rate frozen in time, a baseline to compare with more recent measurements. And here's where things get fascinating. This ancient light tells a slightly different story than the stars and galaxies we see today, creating one of cosmology's biggest headaches, the Hubble tension. To understand how this works, picture the CMB as a ruler etched into the sky. The size of those temperature fluctuations we've discussed, those tiny hot and cold spots, acts like mile markers. Since we know how sound waves traveled through the early universe's plasma, we can calculate how far apart these markers should appear. But as the universe expands, those apparent distances stretch, changing the angle these spots subtend in the sky. Planck's meticulous measurements of these angles revealed an expansion rate of about 67 kilometers per second per megaparsec. That means for every 3.26 million light-years you look deeper into space, galaxies appear to be receding 67 kilometers per second faster. The problem arises when we measure the Hubble constant using other methods, like observing pulsating stars called Cepheids or exploding supernova in the nearby universe. These techniques consistently give a higher value, around 73 kilometers per second per megaparsec. At first glance, the difference seems small, but over cosmic distances, it adds up to a glaring discrepancy. It's like checking two watches set to the same time and finding one ticks noticeably faster. Something fundamental must be off. This tension between early universe CMB measurements and late universe observations has sent cosmologists back to the drawing board. Could there be unseen physics at play? Maybe dark energy isn't constant but evolves over time, accelerating expansion more recently than we thought. Or perhaps the universe isn't as uniform as we assumed, with giant voids or concentrations of matter subtly skewing local measurements. Some have even speculated about exotic particles or modifications to gravity itself. The CMB's stubborn consistency forces us to confront these possibilities, proving it's not just a relic of the past but a tool for probing the universe's deepest unknowns. What makes this puzzle so thrilling is its stakes. If the discrepancy is real and not just measurement error, it means our standard model of cosmology, the very framework we've built from the CMB's pristine data, might be incomplete. The Hubble tension could be the first crack in a dam, hinting at physics beyond our current understanding. Every new CMB map, every refined measurement tightens the screws on this mystery, pushing us closer to either solving it or rewriting the textbooks. Either way, the universe's expansion rate isn't just a number, it's a story, and the CMB holds one of its most crucial chapters. Buried within the cosmic microwave background's subtle temperature patterns is a hidden rhythm, an ancient echo of sound waves that once rippled through the universe's fiery infancy. These are Baryon acoustic oscillations, or BAO, the fossilized vibrations of a time when the cosmos was so dense it could carry sound. Picture the early universe as a vast, seething ocean, with pressure waves racing through the plasma at nearly 2/3 the speed of light. As the universe expanded and cooled, these waves froze in place, imprinting their signature on the distribution of matter and leaving behind a cosmic fingerprint we can still detect today. These oscillations aren't just relics, they're one of nature's most precise measuring tapes. The waves traveled a fixed distance about 500,000 light-years before the universe cooled enough to silence them. That distance, now stretched by cosmic expansion to nearly 500 million light-years, acts as a standard ruler embedded in the fabric of space. By measuring how BAOs appear in galaxy surveys or the CMB's fluctuations, astronomers can gauge distances across the universe with remarkable accuracy. It's like finding a single, universal footstep preserved in stone, letting us measure the growth of the cosmos itself. The story of these sound waves begins in the universe's first moments, when matter and radiation were locked in a fierce tug of war. Photons pushed outward while gravity pulled inward, creating oscillations that sloshed the primordial plasma back and forth. When recombination occurred and atoms formed, the photons finally broke free, leaving the matter behind in a pattern of dense shells, like ripples frozen around a pebble dropped in a pond. Today, galaxies are slightly more likely to form at these shell-like overdensities, creating a subtle, repeating pattern in the large-scale structure of the universe. What makes BAOs revolutionary is their independence from other cosmic distance markers. Unlike supernova or variable stars, which rely on assumptions about brightness, Baryon acoustic oscillations are geometric. They depend only on the physics of sound waves in the early universe, a process so well understood it's virtually free of systematic errors. This reliability has made them a cornerstone of modern cosmology, helping to confirm the existence of dark energy and refine our measurements of the universe's expansion rate. The sheer scale of these oscillations is humbling. Those frozen ripples span nearly 500 million light-years, a testament to the universe's explosive growth during inflation. Yet their regularity is even more astounding. No matter where we look, BAOs maintain the same characteristic scale, a cosmic drumbeat ringing across space and time. By mapping these oscillations in the CMB and comparing them to galaxy surveys, we've constructed a three-dimensional picture of the universe's structure, revealing the invisible scaffolding of dark matter that guides it all. In a way, Baryon acoustic oscillations are the universe's first melody, a song of pressure and gravity composed in the first 400,000 years and still playing out in the arrangement of galaxies today. They remind us that the cosmos isn't just expanding, it's vibrating with the echoes of its own birth, leaving behind a rhythm we're only now learning to hear. Among the countless mysteries woven into the cosmic microwave background, one of the most tantalizing is the possibility that it holds clues to realities beyond our own. Certain anomalies in the CMB's patterns, like large-scale asymmetries in temperature fluctuations or that enigmatic cold spot we explored earlier, have sparked a radical idea: our universe might not be alone. These irregularities could be cosmic bruises, the aftermath of collisions with other universes in a vast, bubbling multiverse. Imagine the early cosmos as a frothing sea of space-time, where neighboring universes occasionally grazed each other, leaving faint scars in the fabric of our own. The multiverse theory isn't just science fiction, it's a natural extension of cosmic inflation. According to some models, inflation isn't a one-time event but an endless process, spawning universes like bubbles in a boiling pot. Each bubble universe might have its own laws of physics, its own constants, even its own dimensions. Most would remain forever separate, but occasionally, two bubbles could collide or brush against one another during their chaotic expansion. If such a collision happened early enough, its imprint might linger in the CMB's subtle distortions, like a fingerprint on glass. The most striking evidence for this wild idea comes from the CMB's so-called axis of evil, a peculiar alignment of temperature fluctuations that defy standard statistical expectations. Instead of being randomly distributed, some larger-scale patterns seem to line up in a way that suggests a directional preference, as if something outside our universe tugged on it during infancy. Then there's the cold spot, that billion light-year-wide anomaly too extreme to explain with known physics. Could it be a universe bruise, a remnant of a glancing blow from another cosmos? Simulations show such collisions would create disk-like patterns of temperature variation features that eerily resemble some of the CMB's unexplained asymmetries. Skeptics argue these oddities could still be flukes, cosmic dice rolls that landed improbably but not impossibly. After all, even in a perfectly random distribution, some clustering is inevitable. But proponents counter that the odds of all these anomalies occurring together are astronomically low, like shuffling a deck of cards and drawing the same royal flush 3 times in a row. The hunt for definitive proof continues, with researchers scouring next-generation CMB maps for specific signatures, concentric rings of temperature variation, abrupt discontinuities in polarization, or other telltale signs of a multiversal handshake. What makes this idea so electrifying isn't just the scale, it's the philosophical implications. If the CMB truly bears marks of other universes, it would mean our entire cosmos is just one page in an infinite library of realities. The microwave background, already a window to our origins, could become a portal to something far grander. Until then, these anomalies remain cosmic whispers, hinting at possibilities as vast as the multiverse itself. The cosmic microwave background's temperature map isn't just a random scattering of hot and cold spots, it's a cosmic symphony, with patterns so mathematically precise they resemble the stitching on a soccer ball. Those fluctuations we've been examining, they're organized into what cosmologists call multipole moments, harmonics of the universe's earliest vibrations, echoing through time like notes from a colossal instrument. The lowest order moments, especially the quadrupole and octupole, form geometric shapes eerily similar to the pentagons and hexagons of a soccer ball surface. It's as if the infant universe was humming a tune and the CMB is its sheet music. These multipoles aren't just artistic curiosities, they're fundamental to how we decode the universe's structure. Think of the CMB as a giant bubble of trapped sound. When the universe was a seething plasma, pressure waves ricocheted through it, much like sound waves echoing in a cathedral. The quadrupole moment, the first harmonic, captures the broadest vibrations like the deepest bass note of a drum. The octupole refines it further, adding complexity like higher musical overtones. Together, they create a pattern of peaks and troughs across the sky, with warmer and cooler regions aligning in geometric formations that mirror the panels of a soccer ball. What's fascinating is how these patterns reveal the universe's acoustics. The size and spacing of the multipoles depend on the speed of sound in the primordial plasma, a staggering 170,000 meters per second, and how far those sound waves could travel before recombination froze them in place. The soccer ball-like shapes emerge because these oscillations were literally ringing through space, with dense regions collapsing under gravity while radiation pressure pushed back, creating a resonant harmony. When photons finally broke free, they preserved these oscillations as temperature differences, giving us a snapshot of the universe's first vibrations. But here's where things get weird. Some of these large-scale multipoles, especially the quadrupole and octupole, are curiously faint compared to what theorists predicted. It's as if the universe's base notes are missing, a cosmic mystery dubbed the low multipole anomaly. Some suggest it's a statistical fluke, others wonder if it hints at something deeper, like the universe's topology being more complex than we thought, perhaps even finite and folded in on itself like a hall of mirrors. Imagine blowing up a soccer ball only to find some panels stitched tighter than others, distorting the expected pattern. This soccer ball symmetry isn't just a pretty analogy, it's a forensic tool. By analyzing these harmonics, scientists can test theories about the universe's shape, size, and even its birth. The Planck satellite's exquisitely detailed maps show the multipoles with such precision that they've ruled out entire classes of inflationary models, narrowing down how the cosmos might have begun. Yet the anomalies linger, reminding us that for all its elegance, the CMB still holds puzzles we've yet to solve. So next time you see a soccer ball, remember, the universe might have been playing its own game long before we ever kicked a ball. The faint glow of the cosmic microwave background won't last forever. As the universe expands at an accelerating rate, that primordial light is being stretched thinner and colder, its whispers growing fainter with each passing billion years. Right now, we're living in a golden age of cosmic detective work, able to detect this afterglow with our telescopes, but future civilizations won't be so lucky. Within 1 trillion years, the CMB will have redshifted into near invisibility, its wavelengths stretched so long they'll blend into the static of empty space. The universe's baby picture, so crucial to our understanding of the Big Bang, will vanish from view, leaving astronomers of the distant future with no direct evidence of how it all began. This slow fade isn't just a curiosity, it's a countdown. The CMB's current temperature of 2.725 Kelvin is already just a whisper above absolute zero, but as dark energy continues pushing galaxies apart, that temperature will keep dropping. In about 150 billion years, the microwave background will have cooled to half its current value. 1 trillion years from now, it'll be 1,000 times colder, its photons stretched into radio waves with wavelengths longer than the observable universe itself. At that point, detecting the CMB would require instruments larger than galaxy clusters, making it practically impossible even for an advanced civilization. The implications are staggering. Every piece of evidence we take for granted, the CMB's temperature fluctuations, its polarization patterns, even its mere existence, will be erased from the observational record. Future scientists might deduce the universe had a beginning through indirect clues, like the abundance of light elements or the large-scale distribution of galaxies, but they'll never see the smoking gun we have today. It's as if the universe is quietly hiding its own origin story, deleting the first chapter before anyone else can read it. What's even more remarkable is how narrowly we've caught this cosmic light show. Had humans evolved just a few tens of billions of years later, a blink in cosmic time, we might have missed the CMB entirely, leaving the Big Bang as nothing more than a philosophical speculation. Our ability to study this radiation isn't just luck, it's a fleeting privilege granted by our place in cosmic history. The same expansion that made the universe habitable is also ensuring that one day, its oldest light will slip beyond our grasp forever. This slow disappearance raises profound questions about knowledge itself. If the universe can erase its own history so thoroughly, how many other cosmic epochs have already vanished without a trace? Are we, too, living in an era whose defining features will one day be lost to time? The CMB's fading glow is a humbling reminder that the universe has no obligation to preserve its secrets. We have to uncover them while we still can. Sometimes the greatest scientific discoveries aren't made by those looking for them, but by those simply persistent enough to solve a problem, even if that problem involves stubborn pigeons. When Arno Penzias and Robert Wilson pointed their radio telescope at the sky in 1965, they weren't hunting for echoes of the Big Bang. They were just trying to eliminate an annoying hiss in their instrument, a hiss so persistent they initially blamed bird droppings. Their Bell Labs horn antenna in Holmdel, New Jersey, had become a favorite roost for pigeons, which left what Penzias diplomatically called a white dielectric material coating the reflector. After repeatedly evicting the birds and scrubbing the antenna clean, the pair expected the noise to vanish, but the hiss remained unwavering no matter where they pointed the telescope. It wasn't interference, it wasn't equipment malfunction, it wasn't even pigeons. What they'd stumbled upon was the faint afterglow of creation itself. This cosmic static baffled them. The signal seemed to come from every direction equally, like an invisible mist filling the universe. Meanwhile, just 30 miles away at Princeton, physicist Robert Dicke and his team had been building a radiometer specifically to search for this very phenomenon, the cooled remnants of a hot, dense early universe. When Penzias called Dicke to describe the mystery noise, Dicke reportedly turned to his colleagues and said, "Well, boys, we've been scooped." The two groups published back-to-back papers in 1965, Penzias and Wilson describing their perplexing discovery, and Dicke's team explaining its staggering implications, that this was the predicted cosmic microwave background radiation, the cooled remnant of the Big Bang. What makes this accidental discovery so extraordinary is how perfectly it fit into cosmology's grand puzzle. At the time, astronomers were fiercely divided between two theories of the universe's origin: the Big Bang and the steady-state model, which proposed the cosmos had no beginning but continually created new matter to maintain its density. The CMB's existence was a definitive prediction of the Big Bang theory. If the universe had once been a searing hot plasma, it would have released a flash of radiation as it cooled radiation that, over billions of years, would redshift into microwaves. Penzias and Wilson's hiss matched those predictions exactly. The steady-state theory couldn't explain such uniform background radiation, and with this single discovery, it crumbled. The sheer humility of this breakthrough is striking. Two engineers with no background in cosmology, armed with a repurposed satellite communications antenna and a broom for pigeon cleanup, had stumbled upon the oldest light in existence. Their meticulous troubleshooting, eliminating every possible terrestrial and instrumental cause, transformed what could have been dismissed as noise into one of science's most profound revelations. It's a reminder that sometimes the universe whispers its secrets to those willing to listen, even if they aren't the ones everyone expects to hear them. The discovery earned Penzias and Wilson the 1978 Nobel Prize in Physics, but its true legacy is deeper. That persistent hiss wasn't just background noise, it was the universe's birth certificate, a signal sent across 13.8 billion years to settle humanity's oldest question: where did it all begin? And to think it might have remained buried in static forever if not for two engineers who refused to ignore a little interference. The photons composing the cosmic microwave background have been traveling longer than stars, galaxies, or even atoms have existed. A staggering 13.8 billion years of uninterrupted flight through an ever-expanding cosmos. When these ancient particles of light finally reach our telescopes, they're delivering a message from the universe's first moment of transparency, a time before planets, before stars, before even the simplest molecules. This light is so old that its origins predate every structure we consider familiar, carrying snapshots of reality when space itself was 1,000 times smaller and 1,000,000 times hotter than today. To grasp the scale of this journey, picture a photon released during recombination. The moment the universe cooled enough to become transparent, that photon might have begun its voyage near what would one day become the Andromeda Galaxy, but back then, everything was compressed into a searing hot plasma, filling a volume billions of times smaller than the present cosmos. As space expanded, the photon raced outward, stretching to ever longer wavelengths while the universe itself transformed around it. Stars ignited and died, galaxies collided, black holes formed, all while this messenger from the dawn of time hurtled forward, undisturbed, until it finally struck the detector of a modern telescope. What's astonishing isn't just the duration of this journey, but how pristine the information remains. Despite traversing nearly the entire observable universe, these photons have interacted with almost nothing along the way. The cosmos is so vast and empty that most CMB light arrives untouched, its properties frozen since the instant it broke free from the primordial plasma. It's like receiving a letter in perfect condition after it's floated across an ocean, except this ocean is space itself, and the letter was written when reality was in its infancy. This unimpeded voyage gives the CMB a uniqueness no other cosmic signal can match. Light from quasars or supernova gets scattered by dust, bent by gravity, or absorbed by gas clouds during its travel. But the microwave background's photons come to us almost exactly as they were 13.8 billion years ago, offering a direct pipeline to the universe's formative moments. When we map their subtle temperature variations, we're not just studying ancient history, we're touching the fabric of time itself. The sheer longevity of this light puts human timescales into humbling perspective. The oldest pyramids are 4,500 years old. Dinosaurs roamed 230 million years ago. Our planet formed 4.5 billion years in the past. Yet the CMB's photons predate all of it by such an immense margin that human civilization's entire existence is less than a heartbeat in comparison. They remind us that we're latecomers to a cosmic story that began long before us, a story written in light that refused to fade. Even more mind-bending is realizing these photons aren't rare. They're everywhere. Every cubic centimeter of space holds around 400 CMB photons, outnumbering atoms by over 1 billion to 1. The light bathing your skin right now includes photons that witnessed the universe's first dawn. They've outlasted epochs, crossed unfathomable distances, and now, after 13.8 billion years, they're ending their journey here with us as we piece together the story they've carried since time began. This light's endurance is what makes it irreplaceable. No future observation, no matter how advanced, will ever capture a younger universe than the one revealed in the CMB. It's the ultimate boundary of our observational horizon, the furthest back we can peer before the cosmic fog of the pre-recombination era obscures everything. These photons are time travelers from the edge of the knowable, and their arrival in our telescopes is nothing short of a cosmic miracle, one that lets us stare directly into the universe's fiery cradle. The cosmic microwave background doesn't just support the Big Bang theory, it demolishes the competition. For decades, rival cosmological models have tried to explain the universe without a fiery beginning, but the CMB's relentless consistency has left most of them in the dust. Take the steady-state theory, once the Big Bang's greatest rival. Proposed in the 1940s, it claimed the universe had no starting point, but instead continuously created new matter to maintain its density as it expanded. Elegant as it was, steady-state cosmology had one fatal flaw. It couldn't explain the CMB's existence. If the universe had always been as it is now, where did this omnipresent microwave glow come from? The theory's proponents scrambled to explain it as scattered starlight from distant galaxies, but the numbers never added up. The CMB's near-perfect blackbody spectrum and staggering uniformity pointed to a single, explosive origin, a Big Bang. Plasma cosmology, another alternative, fared no better. This model suggested that electromagnetic forces in ionized gases, rather than gravity, shaped the universe's large-scale structure. But when confronted with the CMB's precise temperature fluctuations patterns that perfectly match gravitational collapse models, plasma cosmology's explanations grew convoluted. Why would electromagnetic processes create density variations that just happen to align with what gravity would produce? The CMB's acoustic peaks, those frozen sound waves from the early universe, bear the unmistakable signature of gravitational tug-of-war between matter and radiation, not plasma dynamics. It's like finding a fingerprint at a crime scene that only matches one suspect's hand. Even more exotic theories, like the tired light hypothesis, which claimed redshift results from photons losing energy over time rather than cosmic expansion, crumble under the CMB's scrutiny. If light simply tired with distance, the microwave background wouldn't display a perfect blackbody spectrum. Instead, we'd see a distorted smearing of wavelengths, like a song played on a warped record. But the CMB's spectrum is so pristine it's been called the most perfect blackbody ever measured, a bullseye for Big Bang predictions. What makes the CMB such a devastating weapon against alternative cosmologies isn't just its existence, it's the precision of its predictions. The Big Bang model didn't merely guess there'd be leftover radiation. It calculated the exact temperature that radiation should have today, 2.725 Kelvin, decades before Penzias and Wilson found it. It predicted the spectrum's shape, the size of its fluctuations, even how those fluctuations should be distributed. When rival theories are forced to retrofit explanations for these phenomena after the fact, their patchwork solutions strain credibility. The CMB isn't just evidence, it's a litmus test, separating theories that truly explain the universe from those that merely accommodate it. This isn't to say science should discourage competing ideas. Every great theory thrives when challenged, but after 60 years of observation, the CMB remains the gold standard because it does what all good evidence should: it eliminates guesswork. While alternative models twist themselves into knots trying to explain one anomaly after another, the Big Bang's framework keeps turning the CMB's whispers into revelations. From dark matter's gravitational fingerprints to dark energy's subtle stretching of space, the microwave background has become a Rosetta Stone for cosmic mysteries, one that only the Big Bang's language can fully decode. The sheer volume of data generated by studying the cosmic microwave background is almost as staggering as the phenomenon itself. Missions like Planck and WMAP didn't just capture pretty pictures of the sky. They produced oceans of raw numbers so vast that researchers needed entire server farms just to store and process it all. Think about this: Planck's final data release in 2018 amounted to over 10 petabytes, that's 10 million gigabytes, enough to fill 20,000 high-end laptops. Every subtle fluctuation, every polarization twist, every nanometer shift in wavelength was recorded with such precision that analyzing it required not just computers, but supercomputers capable of crunching quadrillions of calculations per second. To grasp why the CMB demands this computational firepower, picture trying to listen to a single violin playing in a hurricane. The microwave background signal is extraordinarily faint, buried under layers of interference from our own galaxy, nearby stars, and even Earth's atmosphere. Separating the universe's first light from this cosmic static is like reconstructing a whisper from a cacophony of screams. Each pixel in Planck's sky maps represents countless hours of observation, calibration, and algorithmic filtering to isolate the true CMB signal from contamination. The satellite's detectors were so sensitive they could distinguish temperature variations as small as 1/1,000,000th of a degree, requiring data pipelines so complex they took years to refine. The numbers behind these missions boggle the mind. Planck scanned the entire sky 8 times over its 4-year mission, its detectors logging over 2.5 trillion individual measurements. Processing this deluge meant developing entirely new statistical techniques, some of which are now used in fields from medical imaging to financial forecasting. Teams of coders wrote algorithms to clean the data of noise like galactic dust, then ran simulations on supercomputers to compare thousands of possible universe models against the observations. The result, a map so precise it revealed details 100 times finer than WMAP, sharpening our view of cosmic history like upgrading from blurry binoculars to the Hubble Space Telescope. What's fascinating is how these data challenges push technology forward. analyzing the CMB's faint whispers led to breakthroughs in signal processing that now help detect gravitational waves and filter noise in quantum computers. The machine learning tools first developed to spot patterns in Planck's day now power everything from weather prediction to self-driving cars. Even the compression algorithms used to shrink those 10 petabytes into something manageable have revolutionized how we stream high-definition video. The cosmic microwave background isn't just teaching us about the universe, it's reshaping how we handle information itself, and the data keeps coming. Next-generation experiments like the Simons Observatory and CMBS-4 will generate even more staggering amounts of information petabytes per year as they hunt for the elusive B-mode polarization that could confirm cosmic inflation. These projects will rely on exascale computing, the next frontier in processing power capable of a quintillion operations per second. It's a cosmic irony. To study the universe's simplest light, we've had to build some of the most complex machines in human history. The CMB's whispers may be ancient, but decoding them requires every bit of our cutting-edge present. Could the cosmic microwave background be hiding clues to dimensions beyond our own? Among its subtle anomalies, some scientists suspect whispers of a reality more vast than we've ever imagined, one where space isn't just three-dimensional, but curled into unseen folds predicted by string theory. If true, these extra dimensions, too tiny to notice in everyday life, might leave faint fingerprints in the CMB's patterns, warping how gravity propagated in the early universe and distorting the microwave background in ways we're only beginning to detect. String theory's vision of higher dimensions isn't science fiction. To reconcile quantum mechanics with gravity, it proposes that the universe has 10 or 11 dimensions, with all but the familiar 4 length, width, height, and time tightly coiled at scales a billion times smaller than an atom. But during inflation, when space-time stretched exponentially, these hidden dimensions might have vibrated like plucked guitar strings, sending ripples through the fabric of reality. Those ripples could have subtly altered how gravity shaped the early universe, imprinting telltale asymmetries in the CMB's temperature fluctuations or polarization patterns. The most promising place to hunt for these cosmic breadcrumbs, the CMB's largest scale anomalies, certain asymmetries in the microwave background like the mysterious alignment of temperature fluctuations along an axis of evil or the unexplained cold spot, don't fit neatly into standard cosmology. Some theorists suggest these could be shadows of gravity leaking into extra dimensions during the universe's infancy, a process that would slightly alter how matter clumped together in specific regions. It's like hearing an echo in a room that shouldn't have one, hinting at hidden corridors just beyond perception. Even more tantalizing are distortions in the CMB's polarization. If extra dimensions exist, they'd affect how gravitational waves from inflation propagated, twisting the polarization of light in ways distinct from standard physics. Future telescopes hunting for primordial B-modes could stumble upon these twists, a signature no conventional theory could explain. Imagine finding a locked door in a house you've lived in for years, only to realize it's always been there, just invisible until now. Skeptics argue these anomalies could still be statistical flukes or artifacts of incomplete data. After all, the CMB's patterns are fiendishly complex, and noise from galactic dust or instrumental errors can mimic exotic physics. But proponents counter that as measurements grow sharper, the anomalies persist, nudging us toward explanations beyond the standard model. The CMB isn't just a relic, it's a cipher, and extra dimensions might be its most thrilling unsolved equation. What's at stake isn't just academic. Confirming extra dimensions would revolutionize physics, offering a bridge between quantum mechanics and gravity while rewriting our understanding of reality itself. The CMB, that ancient glow we've mapped with such precision, might hold the key if we learn to read between its microwaves, and if we're right, the universe isn't just bigger than we imagined. It's deeper, stranger, and more interconnected than we ever dreamed. If you've ever pressed your finger to a scanner, you know how uniquely its ridges and swirls identify you. Now picture the entire universe doing the same, leaving behind a cosmic fingerprint in the form of the cosmic microwave background's temperature fluctuations. Those intricate patterns of warmer and cooler spots aren't just random noise, they're a one-of-a-kind signature, a celestial ID card etched into the sky. Just as no two human fingerprints share the same arrangement of loops and walls, no two universes, even in an infinite multiverse, would ever produce identical CMB maps. The odds are astronomically against it. Every twist, every cluster of hot and cold regions is a frozen snapshot of quantum jitters from the universe's first moments, amplified by inflation into a pattern as unique as a snowflake. Think of it like rolling dice across the cosmos. During inflation, quantum fluctuations in energy density were stretched to cosmic scales, imprinting slight variations in the primordial plasma. These variations became the seeds for the CMB's temperature differences we see today. But here's the catch: the exact arrangement of those fluctuations depended on a chaotic dance of probabilities at the quantum level. Even if another universe had nearly identical physical laws, the randomness inherent in those early moments would guarantee its CMB looked different. It's the difference between two hands drawing the same shape. The broad strokes might resemble each other, but the microscopic details will always diverge. This uniqueness isn't just theoretical. The CMB's patterns are so finely detailed that scientists can calculate the mind-boggling improbability of replication. The Planck satellite mapped over 4,000 distinct fluctuations across the sky, each with its own slight temperature variation. The number of possible arrangements for these patches exceeds the number of atoms in the observable universe. That's how precise this cosmic fingerprint is. If the multiverse exists, each bubble universe would carry its own version of the CMB, with fluctuations as distinct as siblings' fingerprints, similar in general structure but never identical. What makes this idea so electrifying is its implications. If we could somehow peer beyond our universe and compare CMB maps, their differences would reveal how wildly inflation's quantum dice rolled elsewhere. A slightly colder spot here, a warmer cluster there, these tiny divergences would encode alternate cosmic histories, like genetic variations in twins. Some universes might have stronger fluctuations, leading to more clustered galaxies. Others might be smoother, their galaxies sparse. The CMB isn't just our universe's birth certificate, it's a manifesto declaring its individuality. And just like forensic experts can reconstruct a suspect's habits from fingerprint ridges, cosmologists decode the universe's infancy from these microwave patterns. The colder spots hint at regions where matter was slightly denser, the warmer ones where it was sparser. Over billions of years, gravity tugged on these differences, sculpting the cosmic web of galaxies we see today. Your existence, the shape of your home galaxy, even the distribution of stars in the night sky, all of it traces back to those unique fluctuations. We're literally made from a fingerprint no other universe shares. So the next time you hear about the CMB's temperature map, remember, you're not just looking at data, you're staring at the universe's signature, a self-portrait it painted in microwaves at the dawn of time. And if the multiverse is real, that portrait is hanging in a gallery of infinite variations, each one as singular as you are. The cosmic microwave background isn't just ancient, it's a relic from a time before starlight even existed, a whisper from the universe's darkest chapter. When this light first broke free, the cosmos was a vast, starless void, shrouded in a fog of hydrogen gas so thick it would take another 200 million years for the first stars to pierce through. Imagine a world without constellations, without galaxies, without any source of light except the fading afterglow of creation itself. That's the era the CMB captures, the cosmic dark ages, a period longer than the entire reign of the dinosaurs, stretching between the universe's fiery birth and the dawn of its first luminous objects. To grasp how profound this is, consider the timeline. The CMB dates back to just 380,000 years after the Big Bang, while the first stars didn't ignite until around 200 million years later. That means the photons hitting telescopes today spent an eternity traveling through a pitch-black universe, untouched by the glare of suns or the glow of galaxies. They're messengers from an era when space was utterly, unimaginably dark, a darkness so complete it's hard to fathom in our glittering night sky. This primordial gloom wasn't just eerie, it was transformative. During those millions of years, gravity worked in silence, slowly pulling matter into denser clumps. The slight overdensities imprinted in the CMB's temperature fluctuations, those 1 part in 100,000 variations, were the only seeds in an otherwise barren cosmos. Without the light of stars to ionize the gas, the universe remained a neutral hydrogen sea, a blank canvas waiting for its first brushstrokes of brilliance. The CMB's light is the last snapshot of that quiet, unlit world, frozen just before gravity's patience paid off and the first stars finally sparked. What's staggering is how much changed between the CMB's release and the universe's first dawn. By the time those earliest stars, known as population Roman III stars, ignited, the cosmos had expanded so dramatically that the CMB's temperature had plummeted from 3,000 Kelvin to barely 50. Space itself had grown 1,000 times larger, diluting the primordial plasma into near nothingness. And yet, those first stars didn't just light up the darkness, they shattered it. Their intense ultraviolet radiation ripped electrons from hydrogen atoms, reionizing the universe in a process that took hundreds of millions of years. The CMB carries no memory of this upheaval. It's a time capsule sealed before the fireworks began. This gap between the CMB's emergence and the first starlight is one of cosmology's most tantalizing mysteries. We've never directly observed those first stars. They're too faint and distant for current telescopes. But the CMB gives us clues. By studying how its photons polarized as they interacted with the earliest atoms, scientists can trace the timeline of reionization, like detectives reconstructing a crime scene from scattered fingerprints. The James Webb Space Telescope, peering into the infrared, is now hunting for glimpses of this epoch, bridging the gap between the CMB's pristine glow and the star-filled cosmos we know today. The irony is poetic. The CMB, a relic of light, comes from a time before light as we know it existed. It's a beacon from the darkness, a reminder that the universe's story didn't begin with stars, it began with their absence. And those photons, older than every galaxy, every supernova, every flickering candle in the night, have outlasted them all, carrying their ancient message across the ages to us. They're not just light, they're the last echoes of a silent universe, one that waited patiently in the dark for its first dawn. Einstein's theory of general relativity has passed every test we've thrown at it for over a century, from bending starlight around the sun to explaining the dance of binary pulsars. But the grandest laboratory for testing its predictions isn't on Earth or even in our galaxy. It's the cosmic microwave background, a sprawling cosmic experiment that puts relativity through its paces on scales Einstein himself could hardly have imagined. The CMB's near-perfect isotropy, its uniform temperature in all directions, isn't just a curiosity. It's a stress test for gravity's behavior across billions of light years. If general relativity had faltered at these extremes, if space-time curved differently on cosmic scales than around planets, the CMB would bear the scars. Yet 13.8 billion years after the Big Bang, Einstein's equations still hold the universe together flawlessly. Picture gravity as a sculptor shaping the cosmos. According to general relativity, massive objects warp space-time, and those distortions guide how matter and energy move. On Earth, this means apples fall from trees. Across galaxy clusters, it creates gravitational lenses that bend light. But in the early universe, gravity's role was even more profound. It orchestrated the CMB's temperature fluctuations by tugging at the primordial plasma. The patterns we see today, those subtle hot and cold spots, are essentially gravity's handwriting, a signature of how space-time curved when the universe was a seething, opaque soup. When cosmologists compare these patterns to relativity's predictions, the match is uncanny. The way galaxies cluster, how light redshifts over cosmic distances, even the universe's expansion rate, all of it aligns with Einstein's vision, with the CMB serving as the ultimate calibration tool. What makes this validation so striking is the sheer scale. General relativity wasn't designed with a 13.8 billion-year-old, ever-expanding universe in mind. Einstein originally introduced the cosmological constant as a fudge factor to keep the cosmos static. Yet when we apply his equations to the CMB's acoustic peaks, those frozen sound waves from the early universe, they predict the exact spacing and amplitude we observe. It's like using a century-old blueprint to build a skyscraper 1,000 miles tall, only to find every beam and bolt slots perfectly into place. Even phenomena Einstein never dreamed of, like dark energy's accelerating push, leave traces in the CMB that align with relativity's framework when tweaked with that once maligned cosmological constant. The CMB doesn't just confirm relativity, it narrows the wiggle room for alternatives. Theories like modified Newtonian dynamics (MUND), which tweak gravity to explain galactic rotations without dark matter, struggle to replicate the CMB's precise fluctuation patterns. String theory's higher dimensions or quantum gravity models must also bend to the CMB's constraints, ensuring any deviation from Einstein's vision remains vanishingly small. This doesn't mean relativity is perfect. It famously clashes with quantum mechanics, but it does mean that if gravity behaves differently on cosmic scales, the difference is so subtle that even the CMB's exquisitely sensitive maps can't spot it yet. Perhaps the most profound test lies in the CMB's polarization. Gravitational waves from inflation, if they exist, would twist this polarization in ways dictated by relativity. When BICEP 2 claimed a detection in 2014, later attributed to dust, the excitement wasn't just about proving inflation. It was about seeing if gravity waves propagated exactly as Einstein predicted across 14 billion years of expanding space. Future experiments like CMB-S4 aim to settle this with even finer measurements. The CMB's verdict, so far, Einstein reigns supreme. From the largest scales of galaxy clustering to the infinitesimal ripples of quantum fluctuations stretched across the sky, general relativity remains the universe's chosen language for gravity. And every new CMB map is like a cosmic report card, grading that theory not just on Earth or in our solar system, but across the entire observable universe. If there's a crack in relativity's foundation, it's hiding in places even the CMB's ancient light hasn't yet illuminated. Hidden in the faint whispers of the cosmic microwave background could be the universe's best-kept secret, the missing link between Einstein's gravity and the bizarre realm of quantum mechanics. For decades, physicists have struggled to reconcile these two pillars of modern physics, with general relativity governing the cosmic scale and quantum rules dictating the atomic. But what if the CMB holds clues to how these worlds collide? Future telescopes, armed with unprecedented precision, might soon spot the subtle scars left by quantum gravity on the oldest light in existence, imprints so tiny they've eluded detection until now. Consider this: in the first fraction of a second after the Big Bang, when the universe was smaller than an atom, gravity wasn't the smooth force we know today. It was a seething quantum foam where space and time themselves churned unpredictably. Inflation's explosive expansion should have magnified these microscopic tremors, stretching them across the cosmos and freezing them into the CMB's polarization patterns. The telltale sign, a faint, swirling distortion in the microwave background's B-mode polarization, distinct from the twists caused by inflationary gravitational waves. Spotting this signature would be like finding a fingerprint on a relic, proof that gravity, too, plays by quantum rules when pushed to extremes. The challenge lies in the scale. Quantum gravity's effects are thought to imprint at magnitudes a billion times smaller than the CMB's known fluctuations. Detecting them would require instruments sensitive enough to measure temperature variations of a billionth of a degree and polarization angles smaller than 100th of a degree. Projects like the proposed CMB-HD aim to achieve this by deploying arrays of superconducting detectors in the ultra-dry air of the Atacama Desert or Antarctica, scanning the sky with resolutions sharper than ever before. It's the equivalent of trying to spot a single grain of sand on a beach from orbit, except the beach is the entire observable universe. What makes this hunt so electrifying is the possibility of stumbling upon physics beyond our wildest theories. String theory, loop quantum gravity, and other frameworks each predict slightly different quantum gravity imprints in the CMB's polarization. A detection could rule out entire classes of models, narrowing the path toward a unified theory. Imagine if the CMB's patterns revealed that space isn't continuous but pixelated at the tiniest scales, like a cosmic photo blown up to reveal its digital grid. Or that gravity leaks into extra dimensions, subtly altering how primordial gravitational waves propagated. These aren't just abstract ideas, they're potential realities waiting in the data. Even failure would be illuminating. If the CMB shows no trace of quantum gravity, it could mean the effects are fainter than predicted or that our theories need radical rethinking. But the mere possibility that the universe's first light might encode the solution to physics' greatest puzzle is enough to keep scientists scanning those microwaves. After all, the CMB has already rewritten cosmology once, who's to say it won't do it again, this time revealing the quantum heartbeat beneath spacetime itself. The term Big Bang, now synonymous with the birth of the universe, started as a joke, a sarcastic jab from one of the theory's most vocal critics. British astronomer Fred Hoyle coined the phrase during a 1949 BBC radio broadcast, dismissing the idea of a sudden cosmic origin as absurd. These theories were based on the hypothesis that all the matter in the universe was created in one big bang at a particular time in the remote past, he quipped, his tone dripping with skepticism. Hoyle, a staunch supporter of the rival steady-state theory, which proposed an eternal, unchanging universe, never imagined his derisive nickname would stick. But history has a way of ironies, because 16 years later, the discovery of the cosmic microwave background didn't just validate the Big Bang theory, it turned Hoyle's mocking phrase into its triumphant banner. What makes this twist so delicious is how perfectly the CMB embodied the explosive universe Hoyle ridiculed. That faint microwave glow wasn't just evidence of a hot, dense beginning, it was the smoking gun. By the time Penzias and Wilson stumbled upon the CMB in 1965, Hoyle's steady-state model was already on shaky ground, but the CMB's blackbody spectrum and all-pervasive uniformity delivered the knockout punch. Here was radiation predicted by George Gamow and colleagues in the 1940s as a relic of the universe's fiery youth, a direct consequence of matter and energy bursting forth from an unimaginably compact state. Hoyle's Big Bang label, meant to evoke something crude and unscientific, became the perfect descriptor for the most elegant cosmological framework in history. The CMB's role in this naming drama goes deeper than just vindication. Hoyle's phrasing inadvertently captured the theory's most mind-bending implication, that time, space, and all physical laws had a starting point. Before the Big Bang concept took hold, even Einstein had resisted the idea of a cosmic genesis, tweaking his equations to avoid it. But the CMB's whispers forced scientists to confront a universe with a definitive origin, one where nothing preceded something. Hoyle's dismissive term, stripped of its sarcasm, became a linguistic vessel for this paradigm shift, a shorthand for the moment. Science embraced the universe's birth cry. Ironically, Hoyle never fully conceded. Even as the CMB evidence mounted, he clung to modified versions of steady-state theory, proposing exotic mechanisms like mini-bangs to explain the radiation. But the scientific consensus had moved on, and the name he'd intended as an insult was now etched in textbooks. There's poetic justice in how the universe itself, through the silent testimony of the CMB, had the last laugh, transforming a skeptic's sneer into the defining metaphor for cosmic creation. Today, the term Big Bang is so entrenched that few remember its origins as a linguistic grenade tossed in a theoretical battle. And that's the true power of the CMB. It didn't just settle a debate, it reshaped language, turning a punchline into a cornerstone. Every time we say Big Bang, we're unknowingly honoring the CMB's quiet triumph, a reminder that even the universe's oldest light can rewrite history in the most unexpected ways. The cosmic microwave background isn't just light, it's a time machine, a portal to energies so extreme they make particle colliders look like toys. This ancient glow lets astronomers peer back to a trillionth of a second after the Big Bang, an epoch when the universe was hotter than the core of a supernova and denser than a neutron star. No lab on Earth can recreate these conditions, but the CMB preserves their fingerprints like a cosmic fossil. Every photon carries encoded details about physics at energies a quadrillion times beyond what the Large Hadron Collider can probe. It's as if nature left us an encrypted hard drive from the universe's first moments, and we're just beginning to crack the code. Take inflation, the theorized exponential expansion of space in the universe's first sliver of time. The CMB's near-perfect uniformity and specific fluctuation patterns serve as its only direct evidence. These patterns match what you'd expect if quantum fluctuations were stretched to cosmic scales, like microscopic ripples blown up to the size of continents. But here's what's staggering. Inflation occurred at energies around 10 to the 16th power GeV, a scale where gravity and quantum forces may have unified. That's 10 trillion times more energetic than the LHC's maximum collisions. Without the CMB's snapshot of this era, we'd have no observational way to test these ideas. The microwaves bathing our telescopes are literally the only surviving witnesses to physics at energies we'll never replicate. Even more mind-bending is how the CMB constrains hypothetical particles. Actions, sterile neutrinos, or extra-dimensional gravitons, if they existed in the early universe, they'd have subtly altered how plasma clumped before recombination. The CMB's fluctuation spectrum acts like a cosmic spectrometer, its peaks and troughs ruling out entire families of particles that fail to match its precise measurements. It's already eliminated certain dark matter candidates simply because their predicted interactions would have distorted the microwave background more than observed. Imagine sifting through a sand dune to find a single grain that doesn't belong. That's the level of discrimination the CMB provides. The true power of this time machine lies in its dual nature. It's both a microscope for quantum gravity's domain and a telescope for cosmic evolution. The same polarization patterns that might reveal primordial gravitational waves also encode the exact moment when the first atoms formed. Its temperature fluctuations narrate both the universe's fiery birth and the slow crescendo of galaxy formation. No other phenomenon in astronomy spans such a chasm of scales, linking the infinitesimal to the infinite. What's humbling is realizing how much we still don't know. The CMB has answered foundational questions about the universe's age, composition, and geometry, yet its deepest mysteries may require instruments not yet imagined. Future telescopes could uncover signs of pre-Big Bang physics or evidence of cyclic universes in its polarization. For now, this glow remains our clearest window to time's origin, a reminder that sometimes the most profound truths come dressed in microwaves. From the universe's baby picture to whispers of parallel dimensions, the cosmic microwave background has rewritten our cosmic story in ways even its discoverers couldn't have imagined. Let's take one final journey through these 25 revelations, how this ancient glow is older than atoms, colder than starlight, and everywhere at once, even passing through you right now. It's the echo of inflation's thunderclap, the fossilized sound waves of creation, and the ultimate time capsule from when space itself was 1,000,000 times hotter than the sun. The CMB betrayed dark matter's grip, measured dark energy's push, and proved the universe isn't just expanding, it's flat, infinite, and humming with quantum secrets. It transformed an insult like Big Bang into science's greatest triumph and turned pigeon interference into a Nobel Prize. This radiation predicted galaxies before they existed, outlasted every star, and may yet reveal cracks in Einstein's relativity or hints of higher dimensions. And though its light is fading into cosmic static, we've captured its whispers just in time, proving that sometimes the universe's most profound truths come disguised as background noise. But the story isn't over. Every anomaly, the cold spot, the axis of evil, the missing multipoles still taunts us with unanswered questions. Could these be clues to multiverses, quantum gravity, or physics we've yet to dream of? That's the magic of the CMB. The more we learn, the deeper the mysteries grow. So tell us, which of these cosmic riddles fascinates you most? Is it the universe's hidden fingerprint, the battle between dark forces, or the light that's older than time itself? Drop your thoughts below, and if this voyage to the edge of space-time left you hungry for more, hit that subscribe button. We've got endless space mysteries waiting to unravel. After all, the CMB taught us one thing above all: the universe never runs out of surprises.